For problem number 3, we've got a 36-volt battery, 4 resistors, and a capacitor. And right now we have the switch open. So the capacitor is disconnected from the circuit. The first thing that I'm going to do, because I like working with vertical circuits, is to recreate this circuit vertically, and I'm going to start by eliminating the capacitor since the switch is open. So I've got 36 volts. It goes through a 3 ohm resistor, and then I hit a branch that goes off into 9 ohms, and then 6 and 12 in series. So as I hit this branch here, I can see that these are along the same wire. And then they come back together at this point and reach the opposite side of the battery. So it's always easiest to figure out the net current if you can figure out the equivalent resistance. So these are in series. I just add them together. And then the 9 and 18 are in parallel, so I get 1 over 9 plus 1 over 18 to get 3 over 18, and that gives me 6 ohms. And then just to, again, redraw the circuit so you can see how these are substituted, I have my 3 ohm that I have not yet touched, and then I added all of these resistors together to get 6 ohms. And in total, I have an equivalent resistance of 9 ohms. So this will help me to get the net current. The net current is going to go out of the battery and through the 3 ohm resistor. And so I can solve for I, given that voltage is 36 and equivalent resistance is 9. So 36 divided by 9 is 4 amps. So that's the electric current through the battery or in the battery for part A. And then we need to figure out the current through the 12 ohm resistor. So what we notice is that the 4 amps, so it's good to label the current, is going to split off into 2 different currents. We call it I2 and I3 if this is I1. And we know that based on the junction rule, that I1 is equal to I2 plus I3, or 4 is equal to I2 plus I3. Now, unfortunately, we would have to do one step prior to figuring out any of these current values, and that would be to identify, so let me clear out some of this, identify the voltage drop through this resistor. And obviously, the easiest thing to do first is get the voltage drop through the 3 ohm resistor. So the 3 ohm resistor has a voltage of VIR, so it's 4 amps times 3 ohms, so that's going to give us 12 volts. And then the 9 ohm resistor takes it all the way back to this battery, therefore the rest of the 36 volts has to be dissipated by the 9 ohm resistor. So if I used up 12, then that means I have 24 volts left to get to 0. So knowing and here's my VIR triangle because that is always helpful. Knowing 2 out of the 3 variables in the VIR equation, you can solve for the third. And the fact that I have resistance and I have voltage means that I can solve for I2. So I2 is equal to 24 divided by 9. Unfortunately, that's going to give me, let me just erase this. That's going to give me a fraction, but that's fine. 8/3 of an amp is I2. And then I already, based on the junction rule, can figure out I3. I3 is the current that's going through the 12 ohm resistor. So if 4 is my total current and 8/3 is my current through I2, then I can solve for I3. So I just do the subtraction. I3 ends up being 4/3, and the current then through 12 is 4/3 of an amp. Voltage drop across 12. So if this is 4/3, it's going to be 4/3 all the way across, which means that 4/3 of an amp is going through the 12 ohm resistor. We know that the voltage is equal to IR, so 12 times 4/3. And 3 reduces with the top 12, that gives you 4 times 4, which is 16 volts. So now we've got 16 volts for the voltage drop across our resistor. So I've got a lot of mess here, but the video hopefully helps you follow kind of my reasoning. I want to move this to this side and this over on that side. And then I can show, let's do it in a different color, that this has a voltage drop of 16 volts. Okay. At this point, the switch is closed. When the switch is closed, then I've got a 5 microfarad battery attached in parallel to the 12 ohm resistor. I already calculated that the voltage drop through the 12 ohm resistor was 16 volts. And if my capacitor is in parallel with that 12 ohm voltage, then that also is going to absorb a voltage of 16 volts. Sometimes it's easier to see in our diagram, so I'm going to delete all of this right here and attach, this is my 12 ohm resistor. I'm going to attach my capacitor to it, and then that shows that they are in parallel. So the charge on the capacitor, here's another equation that's good to know. Voltage is also equal to charge over capacitance. So I use a triangle for this one also. VC. And so the charge equation, let me do D down here. Charge equation is equal to voltage times capacitance. So the charge is going to be 16 volts times 5 times 10 to the negative 6. The answer I get for that is 80 times 10 to the negative 6 coulombs, or 80 microcoulombs. And then the energy stored in the capacitor, this is one of the equations in your equation sheet. 1/2 CV squared is equal to 1/2 5 microfarads. Let me write it out as times 10 to the negative 6 times 16 squared. And that gives you 640 times 10 to the negative 6 joules.